the passion, the energy, the power, the spirit of hardcore.
So my name is Oskar. I'm going to talk to you about, without permission, with programmable cryptography. Briefly about me, independent researcher focusing on programmable cryptography and synology proofs. Previously I worked on mopro, which is this kind of tool stack for making client-side proving on mobile devices easier, as well as Vac.dev, as Michael mentioned, which is kind of a peer-to-peer messaging protocol with a focus on privacy and censorship resistance, and it's also using this synology proof technology I'll talk about. So the TLDR of this talk is, with programmable cryptography, we can permissionlessly reclaim our data. And to understand what it means, we have to understand what I mean by programmable cryptography, as well as reclaiming our data. There's a few takeaways I want you to have from this talk. So first is that programmable cryptography is a very powerful tool. And second is that there's like a lot of cryptographically signed material out there, and we can basically port it and use it where we want. I'll start by sort of giving some motivation and background, and then I'll give a bit of a friendly introduction to synology proofs, and then finally look at some applications. So this was a talk, so this is like a bunch of things that happened like 10, 15 years ago or so. So this was as a talk by Dr. Cory Doctorow at CCC, and he was talking about the war on general purpose computation. And at the time, a lot of the focus was on copyright and so on. But it was also in terms of like lockdown platforms, as the previous speaker was talking about with the Apple ecosystem, but also other environments. And we basically have the same thing going on today. Now I think the focus has shifted a little bit. So it's more towards, for example, things like tornado cache and freedom of speech, where you sort of see this war on general purpose computation and sort of what we can compute, basically. Here's another quote, software eating the world. Also like 15 years ago or so, Mark Andreessen. And that was true back then, but it's even more true now. Like it's obvious to anyone from anywhere that like software is basically running the world. And you can sort of sum this up in terms of like program or reprogrammed, right? So be programmed in the sense of like the algorithm, whether it's some timeline or what have you. And then privacy is dead. We all know this, so I think we can go home. But like, we have basically the same thing going on here. Again, the focus has shifted a little bit, but it's basically the same old stuff. Now, recently, you have things like chat control and sort of Duro being arrested for Telegram, and general sort of war on end-to-end encryption and these types of things. There's more data now, kind of obvious, but like 100 times more data now than like 15 years ago or so. But sort of who owns this data, and what can they do with it, and sort of who owns your data, and what can they compute on? Where is all this data? So a lot of it is obviously stuck in these Web 2 data silos, whether it's your Googles or Facebooks or Amazons, and some is in things like banks or governments. There is like some data that's sort of self-hosted, people running servers at home, or keeping data local. Some is also kind of dark in the sense of being end-to-end encrypted, and some is also having new forms of data, like public blockchains like Bitcoin, where it's sort of a different form of where data being shared and so on. But like this is basically the minority. Like the vast majority of all data is still in these Web 2 silos. So basically, can we use this and basically reclaim our data, where right now it's stuck in these data silos? And basically, there's all this cryptographic matter out there. So I mentioned sort of, obviously, blockchains and end-to-end, that's like one thing that's kind of obvious, where you have all these keys and signatures or whatever. But it's also more traditional things like HTTPS with TLS, emails with DKIM signatures, digital documents with RSA signatures and so on. So it's basically everywhere. And one question is like, can we use this to do things? This is even further back in the 90s. I think this is familiar to everyone or most people here, the crypto wars. And basically at the time, RSA was sort of seen as ammunition, as a weapon, and US sort of banned exports of that. But I mean, because it's just like an algorithm, people put it on t-shirts. Maybe someone has a t-shirt in their basement or something, closet. But that's one of the beauties of cryptography, that you can just use it sort of permissionlessly. And people printed them on T-shirts and so on, so you can't really stop it. And obviously that war was kind of won in the sense that now the modern internet it relies on these kind of things that were at one point in time seen as weapons. And we're kind of in this sort of second phase of crypto wars. If you look at sort of the clampdown on Bitcoin and the other blockchains, as well as things like tornado cash and private money and so on. So we're kind of in the second phase of this. So what I mean by programmable cryptography, so cryptography is about sort of securing digital information, whereas programmable cryptography, you basically add computation on top of that. So examples of tools that are in this kind of family of technologies is CK, so zero-knowledge proofs, MPC, multi-party computation, and FHE, fully homomorphic encryption. And so one example is that you can, for example, prove that you're above the age of 18 using some document, but only revealing that specific fact, not revealing anything else. And one thing I think about these different technologies is that if CK is single player, then MPC and FHE is multiplayer. And there's also other things like witness encryption and so on. So I'll go into a bit about zero-knowledge proofs. This will be like a very high-level friend introduction. So if you're familiar with zero-knowledge proofs, you can zone out, or it can be a bit of a refresher. So basically, zero-knowledge proofs, they allow you to prove arbitrary statements. So it's kind of Turing complete in that sense that anything you want, you can compute on. And it gives you two key properties, so privacy and compression. So privacy is also more formally known as zero-knowledge, and compression succinctness. And examples of both of those sort of properties being used is one is the privacy thing. So I mentioned that you can sort of prove that you're above the age of 18 without revealing anything else. It's also used for like private transactions, like seen in Zcash and Monero and some other systems. And in terms of compression, one classical example of this is proving state changes. So this is common in, for example, layer 2s on Ethereum and so on, where basically you have this other thing going, other sort of parallel chain going on, and then you sort of compress all of those blocks down into like a single short proof that you can put on sort of the primary, the layer 1 blockchain, because then you can sort of prove that all the stages have been correct, and you sort of save, you can have faster transaction confirmations and lower transaction fees and so on. So this is kind of, sounds a bit weird, like how can you do this type of thing? And this is like a toy example of building in some intuition of how this is even possible. So this is this thing called Where's Waldo, where the goal is to find Waldo in this picture. And I can basically prove to you that I know where Waldo is. So how do I do this? So basically imagine I have this as a postcard, and then I put like a larger piece of paper in front of it, and then I make like a tiny hole. And in that tiny hole, the only thing you can see is Waldo and nothing else. And that proves to you that I know where Waldo is because you have just seen Waldo, but you don't actually know where Waldo is on this postcard because I could have it up here or down here. So that's like some intuition of how this kind of thing is possible, but obviously with zero-knowledge proofs, you do this for any kind of statement, and it's sort of built on polynomials and other mathematical tools. So why should you care about this technology? Well, you've all heard this quote, right? Privacy is the power to selectively reveal yourself to the world, from the Cyberpunk Manifesto. Another quote that some of you might be familiar with, but not everyone, is civilization advances by extending the number of operations we can perform without thinking about them, by Alfred Whitehead. And I think there's kind of an interesting property where, because you can create proofs of things and they are like very succinct and you can compose these proofs together, you basically get some kind of friction, you get some certainty about some specific fact, and you can use this as a building block in other systems. So instead of saying like, oh, just trust me, and you have this kind of uncertainty, you have one way of identifying one specific form of certainty, and you can then build on that. And it's kind of how modern society advances in terms of rule of law and stuff. You can sort of trust that things work a certain way. So how does it work? So basically this special program called a zero-knowledge proof. So it's like a normal computer program, but it's a special one. And it's made up of constraints. So one way you think about this is in terms of Sudoku. So Sudoku, you're trying to sort of fill out this grid, right, with like all the rows are 1 through 9, and all the columns have to be 1 through 9, and they have to be unique, and the same thing for the squares. And all of those kind of conditions can be seen as constraints, and all of those constraints have to be true at the same time. And the same thing is true for a zero-knowledge proof. And then you have a prover and a verifier. So the prover is sort of the one that's creating a proof, and then another entity is verifying this, and this can be a person or a computer program, but you can also sort of put this on chain. So for example, that's how it works in Ethereum, where you can actually verify the proof once on chain. And there's some work going into sort of making that possible with Bitcoin, with Opcat and stuff like that. And basically, the prover has this kind of private input as well as public input. So they basically choose what information they want to be private and what information they want to be public. So zero-knowledge proof is quite a sort of new field. The mathematics of it kind of became a thing like basically in the 80s. Back then it was pretty theoretical, but it's only in the sort of the last few decades that, or last 5 to 10 years, that we sort of see an actual uptake of it. And actually making it practical, because these are fundamentally very inefficient, so it's been a lot of effort to make them more efficient and more secure and other affordances. There's also been like a very much of a growing need, especially from sort of blockchains and so on. And this is because they are very complementary technologies, zero-knowledge proofs and blockchains. And obviously a lot of blockchain products are quite well capitalized, which has also spurred on a lot of research in this field. Another thing is also this kind of Moore's law of zero-knowledge proofs. So they start out extremely inefficient, but then basically we see that every 2 years you get like a 10x performance boost. And this is all the way from like kind of fundamental breakthroughs in applied cryptography to sort of hardware acceleration and just more efficient way of solving specific problems. Practically, it sort of got its start about a decade ago with the Zerocache paper, which led into Zcash, which is sort of by Stuco and other cypherpunk. And then later on, you had things like Monero, who started using zero-knowledge proofs in 2018, and after that, it's sort of more and more products have started using them, including multiple people are speaking at this conference. So why zero-knowledge proofs and blockchains? So blockchains, they provide this kind of sensor persistence and transparency, whereas zero-knowledge proofs provide privacy and compression, and they're very complementary. Because in order to get this sensor persistence, you need to have sort of verify things on multiple nodes. But that obviously means that the block space is very scarce, so you don't have like a lot of, you can't put a lot of things on it. But with zero-knowledge proofs, because due to this compression, you have a very small proof that you then can put on chain. And then on the other side, with transparency, which is great in terms of auditability and sort of trust minimization and so on, that also means that your transaction trace, for example, is public. So zero-knowledge proofs, because they provide privacy, allow you to sort of cut that link. So they're very complementary technologies. And this is why you see things like Zcash and Monero on the privacy side, as well as layer 2s in the Ethereum ecosystem and starting now in Bitcoin as well. But we can use zero-knowledge proofs without blockchains, and that's going to be the focus mostly of this talk. So there's a few classes of how you can use zero-knowledge proofs. There's also other people use them for all kinds of crazy stuff. But like one example of how they're used is in terms of private identity and voting, where basically, if you want some kind of Sybil-resistant mechanism, this can be a useful building block for that, and then you want some kind of private voting for that as well. And then, as I mentioned, it's like a lot of Web 2 data that's locked in, and zero-knowledge proofs can be useful there, as we'll see. With all this sort of cryptographic matter that's out there, we can sort of use these existing signatures and so on to do interesting things. So let's look at some more concrete examples. First is SUPAS, which is kind of a crypto-native digital identity system, and then also Open Passport, which is using passport-based data, and then Aadhaar, which is using the digital identity system Aadhaar. So SUPAS is this, I call it like a crypto-native identity. So it was used initially at Susalu, which is kind of similar to sort of parallel society ideals, but it's kind of like a proto-network state, if you will, approaching it from a slightly different angle. And the first one was in Montenegro last year, and since then there's been lots of spin-offs. And basically, they needed a way to sort of have some kind of access control, so sort of showing that you belong somewhere, you can go somewhere, go to the event and so on, as well as do voting in terms of decision making for how things should work at the space. And they basically created this thing that sort of works on mobile and is using called like semaphore and identity commitments and Merkle trees. I'm not going to talk about that in detail, but basically it's a way that you can have some kind of identity, a bit similar to a key pair, and then you can sort of prove things about it and also use it for voting. And this is cool, and people made like games and had like a lot of uptake, including from people who are not very technical, which is like a important thing as well. But it's kind of primitive, so that the synonymous proof, this sort of mechanism is quite simple. And one of the reasons for that is because performance is a problem. So if you look at, for example, layer 2s, they usually do the proving on like a big server, like a server or server farm or whatever. But with these types of things, you want to be able to do it from a phone, which means that it sort of restricts the type of things that you can prove. And the big problem with this is obviously, because it's crypto native, is that like you have to deal with keys and key distribution and so on. So only the people at the event, they have to create the key and they have to have some way of safekeeping it and so on. And there's not a lot of people there, right? So can we use existing key distributions? Yes, so basically instead of using, Supas is using potato hashing, and that's basically a hash method that's specifically, it's CK friendly, so it's made specifically for synonymous proofs, unlike like something like SHA-226. And the reason is because synonymous proofs is basically like a different architecture. So instead of working with binary, it's working on polynomials. So that kind of changes things drastically. So you can do things like SHA-256 in synonymous proofs, but it's like 100 times slower. So it sort of leads to a performance problem. And basically one rule of thumb is that if you want to prove a statement instead of computing it, it's something like 5 orders of magnitude more complex or so, just to give you an idea of sort of what it means to create these kind of synonymous proofs. But that's changing as well and going down, and there's lots of asterisks attached to that. So as I mentioned, we have a lot of cryptographic matter out there. So we have ECD ZKPs for Bitcoin and Ethereum, but then there's other stuff as well, like signed identity documents and emails and so on. So this is Aadhaar. So this is a system called Aadhaar in India. Digital identity system has like 1 billion users, and people use it all the time. So it's basically like a PDF document and it has like your name and address and all this stuff. And people send it like when they apply for a job or a mortgage or what have you. So it's like a very integral part of people's lives. Obviously, it has a lot of problems, right? Because you're revealing all this information to just random people, and there's identity theft and all these kinds of things, which is not great. But it's a product that sort of permissions is taking this system and then wrapping it in the synonymous proofs, and that's called Aadhaar. So basically what that does is that it takes this document, and then because there's an RSA signature in it, you can verify that inside a synonymous proof, and then basically choose which part of this you want to reveal. So you can go all the way from like not revealing anything, just saying that you have a valid Aadhaar identity, or for example, proving that you are part of a certain province, or that your age is between two, like some range or whatever. And also because this is the kind of thing where you want to maintain the privacy of that, but you don't want to outsource that computation. So you want to do it, for example, on a mobile phone for consumers, for this to actually be useful. And this is the kind of thing that was only possible basically last year to make this with a reasonable user experience. Example closer to Europe is this Open Passport product, and it's doing the same thing basically, but with passports instead. So this is like when you go through security or whatever, this has this kind of e-gate thing, and it's kind of checking these types of things. And it's a similar thing, it's kind of usually some kind of RSA signature that you can verify, and then it has different hashing methods and so on. And basically there are different standards, and some are supported and some are not, but it has like quite a lot of uptake. And this is also something that's only possible basically last year or two, where you can basically create this kind of thing and you can prove that you are from a specific country, for example. And this is completely permissionless. It doesn't involve any government or anything. You can just do this because the cryptographic matter exists. people can use all kinds of things like proof of humanity, identity verification, quadratic funding. Basically, when people want some kind of super-resistant mechanism, you need some solution for that. And the design space is quite big, but empirically, what some entities end up using is they end up using some kind of KYC or whatever. And this gives us like one more tool in the toolbox that you can use this kind of technology if you want to, and sort of keep more privacy, so not revealing your name or passport number and these types of things. It can also be used for things like wallet recovery. So if you imagine you have like a multisig, for example, you're probably not going to burn your passport, maybe not in the next 5 years, who knows? We'll see how the nation state is going then. But you can use this as a factor in a multisig, so you can prove that you have access to your passport and then use that as a factor. CK email. So this is another example. And basically, you have this DKIM signature in emails. And it started becoming a thing like about a decade ago. And I think since this year, it's basically mandatory. So you can't really receive an email without the signature. And emails, like, they have a lot of data in them, right? Like, you have your confirmation to join this event, like your ticket. If you're staying in Airbnb or hotel, you have that information as well, your plane ticket. If someone liked your post on Twitter or whatever, like all this information is in your email, and pretty much everyone has an email, right? So basically what you can do is you can use this information, and then it has a signature that you can verify inside a knowledge proof, but then there's this subset of regex that you can use to basically act as a selector. So you can, for example, check that the subject line has some string in it, or there's a specific unique ID, or what have you. And can use this for things like email wallet and ZKPP24. So email wallet is basically, it allows you to send money to another person on an email address. So basically you just send an email, and by that act, the person who received the email, they have a wallet already. And their wallet consists of them controlling that email address. And that's all. So that was kind of the idea with like PayPal in the beginning. You could email people money, but then you had this centralized third party. And here it's literally just you proving that you have access to this email that allows you to have sort of crypto wallets. That's pretty cool. And then ZKPP, it's this trust minimized P2P on-ramp to crypto from fiat, and it's built on top of CK email. So if any of you have ever done any kind of DeFi degen stuff, you might have seen this type of screen where you usually swap between two tokens, except in this case, one of the tokens is USD. And this is running on Venmo. So basically it allows you to sort of send money to someone, and then you have a proof that you have done that, and then you can sort of use that proof to then claim some crypto that belongs to you. And this is something that you do then without KYC or anything like that, and you can do it in 90 seconds. This only works for some specific providers. So basically, in the case of Venmo emails, the reason they started that with that is because it has very rich email confirmation data. So it has a specific identity in it, a specific you can sort of tie it to a specific payment and has a name and stuff that you can't fudge. So that's why it works for that. There's also some other platforms. So I think this is used a bunch in India. It's very much like an alpha product, but it still has like a few $100,000 in volume. So it's like a real thing you can use. Actually, fun note, this Venmo flow stopped working 2 days ago because they changed the format of their email. So that sort of points to the problems of trusting email too much, but it's still like a useful thing you can use. And you can't use it for everything, as I mentioned. So for example, something like Revolut, you can't use it because there's not enough information in the emails. So is there something else we can do? And yes, there is. So what about using TLS? So until now, we've mostly talked about sort of knowledge proofs, but programmable cryptography has sort of more tools in its toolbox. And so the web, it runs on HTTPS and TLS, right? And websites and APIs have extremely rich data, like basically our whole world runs on it. Like if your bank account, it has all your transactions, your tax returns, private messages, everything, right? And TLS provides sort of data origin and integrity, which are vital properties we want, but it doesn't make the data portable. So this leads us into TLS notary. Well, basically the problem is just due to how TLS works with symmetric keys and so on, the client can sort of forge data from the server, so you can't use it directly for a proof. But what you can do instead is you can use MPC, and specifically 2PC, so that's two-party computation. And you have like a notary server, and then basically they do this cryptographic magic, sort of MPC ceremony between them on the TLS session itself. And then they can use this to sort of prove data provenance to a verifier. And this is not like a man-in-the-middle thing. Like the notary service is basically unprivileged. There's nothing special about it. You can use any notary service you want, and you might have like a network of them to sort of get rid of some specific censorship and collusion attacks that exist. And this actually came from a Bitcoin thread, I believe, like 10 years ago or so. So it's been an idea that's been around for a long time, but it's only recently it actually became possible. So ZKPP is using that with Revolut data with like a browser add-on. And I mean, it basically works, right? And this is like a pretty cool thing that it works. It's still a bit rougher on the edges in terms of you needing some kind of add-on and stuff like that, but it works and people are using it. And it's obviously extremely powerful because you can prove basically anything, like access to any information on any website. And I think people are just starting to play around with this stuff. Like it's crazy as possible, but it is, and people are doing it. So a bit more, sort of just briefly give you a bit of an overview on programmable cryptography. So we talked about synod proofs, and they kind of allow you to prove things about your own data, and they're basically like single player. Then you have things like MPC and FHC, and they are multiplayer. So you have you're computing multiple parties on some private information. 2PC, so basically we have two parties, whether it's with MPC or FHC, is kind of the most mature one. There are other sort of things people are using it but it's kind of still requires some breakthroughs in terms of just performance or how you actually set up these systems correctly. You also have combinations, so you can use a CK with combination with FHC and co-snark, so that's kind of like where you have synod proofs and then you do like an MPC together with them, so you can sort of combine these tools. And like one example I didn't talk about here, but one example of FHC is that if you have Alice and Bob, for example, and you want to, let's say you have some embarrassing music taste or something like that, and you want to find out what shared sort of artist or song you like, then you can do this FHC thing called private set intersection, whereby you can find out that, oh, actually we both like this artist together. But one of the problems with that is you can sort of lie, because you can just fill in this set and say, I like everything, and then you reveal some information. So that's why you have to combine these technologies and get the data proven and sort of signed from somewhere. There's other things like witness encryption and I/O, and these are kind of require more fundamental breakthroughs on a sort of more applied math cryptographic level to actually be feasible. But people are playing around with it, and like we're seeing more and more every year. Arguably, you could also include things like smart contract as part of this family. And I think one way of thinking about programmable cryptography is that it's kind of hard and flexible, kind of a bit like bamboo and carbon fiber. So it's kind of hard in the sense of cryptographic hardness and sound money and stuff, but it's also very flexible, so you can use it to interact with all this existing data that exists everywhere. And you can also, another way of looking at it is that because of tie the old world, sort of the bamboo here, and use things like passports and emails and stuff like that, and use that to sort of build something else, like a parallel society. And it's also very futuristic, more like carbon fiber and stuff, where you can use these some tools to basically create alternative systems and hopefully like a better future. So recap, with programmable cryptography, we can permissively reclaim our data. We had like a bit of intro to synod proofs, looked a bit how it worked, and then saw some examples of CK identity, CK email, CKPT, and TLS notary. And yeah, that's it. Here is website if you want to learn more. Go into way more detail into synod proofs and why and how they work and so on, as well as if you want to get your hands dirty and write some code with it. Yeah, thanks.
I'm going to stand up. I stand up here so I can like have you eye to eye. It's really beneficial, the stage. So I think one of the things that has really thrown us all for a curve in our own industry and then communicating the industry's technology to the public is the idea that crypto can only be used for cryptocurrency. And you're postulating here and showing ways that it can be used with other non-cryptographic money systems. Do you see a threat, or threat is probably the wrong word. Is it possible that existing institutions are going to move to ZK technology inside of the KYC regime? So they have all of the customer data, and then they use that for existing more private transactions. And if that's the case, is that a threat then to how it is that non-state currencies, non-state cryptographic proofs and money, is it a competition?
It's a good question. I mean, like any technology, it's kind of a double-edged sword. So we want to allow this kind of thing, but it also means it can be used for bad things. And I mean, that's the case with any technology. For example, maybe you don't want the property that you can prove that you received a private message from someone. Like, that's not necessarily the kind of system we want. But the fact is that the technology allows us to do that. So what we probably want to do instead is we want to design better protocols so that's not possible. And then in terms of uptake in, for example, governments and KYC and stuff, I do think that's definitely possible. I think one way of looking at this technology is that it's orthogonal to blockchains, even though they're very complementary. So people are going to use it for compliance and stuff like that. That's definitely going to be a thing. I don't think it's necessarily a threat. It's more the kind of thing where, I guess I'm more of the accelerationist mindset. Like, I don't think we should sort of stop things. Like, people are just going to do more and more things, but it allows us to create more powerful tools for sort of self-sovereignty, and then it's just a matter of how different entities use that self-sovereignty, just like, I don't know, like how weapons were developed or whatever. Like, that's just like how things work. So I don't think it's something we should be afraid of. I think it's just like people doing stuff and then seeing what happens. And then people can obviously dedicate their attention to specific things that they believe in and use that to build the systems that they want to see. And I think that's what we see happening with projects like Logos and NIM and DarkFi and stuff like that. So I think that's really cool, and we're just going to keep seeing that.
My next question is, and I think that for this audience, it's technical and you can get into it, is, and I forget what's exactly the name of the curve, but it was a long tweet thread that Zuko posted about the explanation of how efficient it is that we can actually get ZK proofs to be in terms of the size of the data, and that we can't necessarily scale Bitcoin on a data availability layer, because really still that the proof size is so large. Yeah.
Yeah.
Is that enough information?
I think I know what you refer to. I have to be honest, I have not spent enough time looking into OPCAT and that kind of thing to know exactly the details of that. I know it's an ongoing discussion, and people have smart ideas how to approach it. I don't know the particulars of that. I would say generally, though, that basically it's a trade-off. So, for example, in the Ethereum world, you have small proofs, but that also has some trade-offs in terms of requiring like a trusted setup and these types of things, and maybe slower proof systems. So what people end up doing is they end up combining systems. So you might have a proof of a proof. So you have like a large proof, and then you basically feed that for something that's very fast, and then you feed that into another proving system that allows you to sort of create smaller proofs. But there's like a lot of innovation here in terms of the cryptographic primitives that's used, as well as sort of if you need to require some new kind of opcode, or if you have some kind of optimistic setup, like BitVM and stuff like that, and there's like a lot of things going on. So there's definitely ways, but then it's a question of what is used, and also what is the I guess acceptance or appetite for kind of, for example, adopting specific opcodes and stuff like that. But I'm not an expert in that. So
I guess the argument is that covenants provide the recursive proof ability, right? And on Bitcoin.
Yes, I believe so. Yeah.
BitVMX. Yeah. So then my last question, and then I'll ask people in the audience. I'll do that right now because I lost it.
So I studied cryptography at the university. We had some lectures about zero knowledge proofs, but it was very mathematical, and the teachers, the academics, they didn't see the use cases. It was like, okay, here are some equations, polynomials, this is how you can prove things, so now you have a new capability, but no one knew like how we could use them. So my question for you is, like if you can run your imagination wild, don't think about what can be done now. What can we build with this technology that was not possible before? Like, do you have some kind of applications in mind? Doesn't have to be related to cryptocurrencies or sense. What can we build with this? If
I mean,
I
think. So some of the example, like private money, like even doing that, private money and cutting transaction graph, that's not obvious you can do. Like often these digital systems, they go sort of, you think that, oh, cash is sort of private, but it's harder to make this private money things. That's one thing. That examples I gave in terms of like ZKPP and TLS notary, which sort of just, that's something that was definitely not possible before. And then I guess in terms of the context you gave, I think that's definitely true. So it's sort of started as this kind of almost theoretical exercise in terms of applied cryptography and stuff, and they were not necessarily thinking about it in terms of what kind of alternative systems can we use. And I think that's something where the blockchain world has sort of shown a new light on it and seen how can we use this technology for other things. And I think if you look at other, like number theory, for example, I forgot which mathematician it was, but he was like bragging that number theory has no use, and that's what makes it amazing. And it turns out it is very useful. So I think it's a kind of similar kind of thing.
I have two ideas in mind. One is probably simpler, which is some kind of spam protection. So you can use the open passport and identity to prove humanity. Maybe there are other, Amir was talking about rate limiting through nullifiers yesterday. But another idea is that is very important in the cryptanarchy space is anonymous reputation. Yeah. So do you have any insight into we can build anonymous reputation systems?
Yeah, it's a good question. I think so one thing that sometimes makes that difficult is a very interesting problem because it's basically like a graph. So you need to be able to, if you have, I don't know, like some eigentrust thing or whatever, where you can prove that, oh, this person gave me this reputation and so on, and have it in a recursive way, so you can use it not just one hop away, but multiple hops away, which is kind of what would make it more useful. That requires sort of things like recursive proofs and requires some of the MPC and FHE stuff. So I think we're starting to see it, but you have to make some kind of trade-off. There's like a trade-off space here where MPC doesn't really work beyond, right now in a practical sense, beyond a certain number of participants. And FHE also has problems with decryption. So you can have many participants, but to decrypt it, you have to all come together and share the key. So that's why people do things like threshold decryption schemes and stuff like that. And it makes it tricky because then you have some kind of semi-trusted thing. So it's a bit gnarly, but I think we're getting better and better tools for that type of thing. But then you can also do things just with the CK as well, where, especially if you can program it, so you could look at something like rate-limited nullifier as a form of reputation system in some sense, because it's just limited in terms of the scope of what it means to have bad reputation, for example. So basically any behavior you can prove or you can use in that type of system. Does that answer your question? Yeah.
Hello, great talk. I have a question regarding formal verification.
Sorry, say again?
I have a question regarding formal verification. So using computer-aided formal verification, we can like prove the Signal protocol or TLS 1.3. Does this also exist for zero-knowledge proofs?
It's a good question. Personally, private phone numbers is like, yeah, this is on my to-do here, I want to check, but it's a problem because so many systems required, so that would be awesome to have some system on that. I'm not familiar with anyone who has actually played around with that, but that sounds like a great hack product to do something on it. It should be possible, I believe. I don't see why it wouldn't be. Maybe someone who's more of an expert in terms of phone numbers, how to actually implement it cryptographically can answer that. But I do think it's possible. I think it would be a fun product. I just don't think anyone has actually played around with it. And you're right, because it's often like the the thing that identifies you online, especially with these KYC registration laws that have ramped up the last decade. Czech Republic here is like a good exception, but I mean, most places in the world, you can't really do it. So it's a big problem. And if someone can solve that, I think that would be amazing.
Oskar,
yeah.
How can you prove humanity?
How we can improve humanity? Prove yeah. Humanity. Okay. So this is the assumption, right? Is that a passport belongs to one person. That's not always the case. It depends on the government and jurisdiction, and there's obviously some exceptions. Let's say you're, I don't know, with some intelligence service, you can probably get more than one passport. But in general, it's a pretty good rule of thumb that like one passport equals one human. So assuming you control your own passport, then you can basically prove that you have kind of a unique identity. And then it's up to you of what you want to reveal with that. But generally, like that's a big problem, for example, in voting systems, where if you want the property that you have one human, one vote, if you can just like create new addresses or like fund them with something, the cryptoeconomic security margin is very low, because if you have some economic stake, that's kind of your margin. But if you require a passport, you can obviously buy passports online and stuff like that, so you can probably put a number on that, but it's at least like something that helps you have some heuristic that this is probably corresponds to a human, and you can use that for voting and other things.
So I have a final question. So we rely a lot on the data availability layer being perpetuated, and I don't honestly think that anybody's shown a economic model for that continuing. And I think that we all understand and assume that client-side proving is very important for the data security aspects of knowing what your own data and your own private key is. Do you think it's possible that we're going to see, I'm going to come back to the centralized entity question of existing state institutions and corporations. Do you foresee us having a period of time where it is that man-in-the-middle attacks or database attacks for data that's being sent through service providers to issue a ZK proof, which is used then inside of the system for identity or for anything happening, or?
That could definitely happen, absolutely, yeah. I think it's the kind of thing where, don't know, like, there's always trade-offs, right? I think this is kind of moving the frontier in terms of capabilities and expressiveness, but then obviously with any system, there's going to have certain weaknesses, and also if people start to rely on these type of technologies more, then that also means that it gets more exposed, there's more reason to hack it and stuff like that. But I think what's cool about this is that you can basically have these multiple sources of information, you can combine them and then use that to get some sort of certainty. But obviously nothing is 100% certain, so there's always going to be something. But I do think the risk of that, or the cost of that, is probably lower than if you just trust something offhand. Like with this, you can at least get some kind of certainty or semblance of certainty that something is the case. Does that answer your question?
Yes, it does. Oskar, thank you so much.
Thank you.